Now we're going to proceed with a more technical discussion and derivation of Feynman's ideas, the Feynman path integral. And I should mention here from the outset that if you're not interested in these technical details, or if you feel that your mathematical background is not sufficient to follow them very closely, you may safely skip this and the following segment because the rest of the course is not going to be heavily dependent on this particular derivation. But otherwise, I would encourage you to actually go through this derivation and maybe even work it out on your own after the lecture, because understanding it would help you develop intuition not only about the path integral itself, but about quantum mechanics more generally. Now, the object that we're going to discuss in this particular segment is so-called propagator, which actually plays an important role in various aspects of quantum theory. But at this level, we can view it simply as an attempt to make quantum mechanics as close as possible to the concepts that we understand intuitively in classical physics. And these concepts involve, for example, the notion of a particle localized in a point in space and the notion of a trajectory that the particle follows. Now, at the operational level, what it is, it involves the following construction. So let's assume that at an initial moment of time t equals 0, our quantum particle was localized in the vicinity of the original point r sub I. So by localized, I mean that its initial wave function psi of 0 t equals 0 is equal to r sub I, this ket vector, which represents the eigenvector of the position operator corresponding to this point. Or in physical terms, it means that this wave function is a very narrow wave packet localized in the vicinity of this r sub I, very similar to the wave packet that we saw in the very first lecture, in the last segment of the very first lecture. And so this initial state is going to evolve under the action of the Schrödinger equation, which is the standard Schrödinger equation with some kinetic energy and potential energy. And as we know from the first lecture, so this evolution, quantum evolution, will involve spreading out of this wave packet with time. So it's, instead of a localized sort of particle-like entity, it's going to become like a cloud surrounding this r sub I, and this spreading out occurs in a very non-trivial fashion in the presence of potential. Now, the question that we're going to ask, and which brings us to this notion of a propagator, is what part of this particle will propagate to a certain final point r sub f. Or, in other words, what part of this spread out wave packet will be located near this point. And this mathematically implies calculating the overlap between the final wave function psi of t, which again is governed by the Schrödinger equation, and this r sub f, which describes a wave packet near this some other final point. So, of course, I don't want to give you the impression that the particle literally propagates from one localized state to another localized state. It does not. It actually spreads out in the quantum mechanical language. But a part of this wave packet will indeed be located near this point, and this is what we want to calculate. And this overlap is the propagator that we're going to focus on. Now, another question that we sort of may ask is how will the particle get there? How will the particle go from the initial point to this partially final point? So this question, strictly speaking, doesn't really make sense in the context of the standard quantum theory based on the Schrödinger equation, because there is really no notion of the trajectory, which implies the ability to measure momentum and coordinate at the same time, which is not possible in quantum mechanics. But as we will see in this different formulation by Feynman, so this question sort of acquires a meaning. And going a bit ahead of ourselves, let me reiterate or advertise again that what we're going to find is that this particle goes from this initial point to a final point, following all possible trajectories that we can possibly imagine. So here are a few of those trajectories that I plotted. Now, to move on to actually calculate this overlap to this propagator, clearly what we need to find is well, the final wave function psi of t. we know the initial condition, we sort of know what the final state we want to get. Now we need to, well, actually solve the Schrödinger equation, which in general is very complicated, but there is a formal solution we can write using the so-called evolution operator. So we're interested in solving the general Schrödinger equation here with some initial condition at t equals 0. So I assume that we know the wave function at the initial moment of time. So this, of course, is a completely general formulation which is not specific to derivation of any path integrals. But, well, in our case, the initial condition we have chosen to be this localized wave packet near a certain point r sub I. So in any case, well, to solve the Schrödinger equation, this time-dependent Schrödinger equation basically means to find the wave function as a function of time, psi of t. And the evolution operator that I just mentioned formally relates the initial condition to the final wave function psi of t. So its action is exactly, in some sense, rotation from psi of 0 to psi of t. I use the word rotation having in mind this geometric picture that we introduced last week to motivate the Dirac notations, you know, this ket vectors psi of t, which in sums are meant to represent a sort of a vector, abstract vector in a linear vector space corresponding to the state of a physical system. Now, if we did have a sort of garden variety linear vector space as our Hilbert space, which normally is very multidimensional, so we can't really draw the axis, but if we imagine for a second that we have, let's say, just 3 axes, and there is a state psi 0, which represents our initial state. So the norm of this vector, so the absolute value squared of this vector, sort of corresponds to the total probability of finding our quantum state, our quantum particle in a certain state. And well, from the Born interpretation, we can say that this probability is equal to 1. We will find the particle if it's there in some state. So the norm of this vector should be preserved as we perform a quantum evolution. So in some sense, the only thing we can imagine this vector doing as a function of time under the action of the Schrödinger equation as is its rotation, you know, by some angle to a certain new state psi of t. And this rotation, the operator which sort of enforces this rotation, is exactly this evolution operator. Again, so here I'm just trying to represent this in an intuitive way. In general, if we're dealing with the generic quantum mechanical problem, there is no way to draw it because we have well, an infinitely dimensional Hilbert space. But still, at some level, this picture is preserved. So this evolution operator rotates a normalized state which describes a particle to a different state which describes the same particle. Now, it turns out that we can actually, instead of writing the Schrödinger equation for the wave function, we can as well just write the same Schrödinger equation for the evolution operator. The only thing we have to do is just to plug in this equation into the Schrödinger equation. We're going to see that we have essentially the identical equation for the evolution operator. So h u of t. And the initial condition for this equation is u of 0 is equal to 1, where 1 is just the identity operator. So why? Well, it sort of follows in a very simple way from its definition. So if we look at this equation, we see that the evolution operator sort of evolves our initial condition to a final state, but, well, if t is equal to 0, there is nothing to evolve. We just stay where we were, and so therefore psi of 0 is equal to psi of 0, so u of t is equal to 1, and this is sort of the initial condition we can enforce. And one can guess in some sense, or just pick a general solution to this matrix or operator equation, which satisfies both the Schrödinger equation itself and the initial condition, by writing u of t as an exponential of minus I over h bar h times t. So, well, at t equals 0, e exponent of 0 is equal to 1, so it does satisfy the required initial condition. And if we plug it into this equation, so if we differentiate this sort of ansatz with respect to time, so well, differentiating the exponential sort of pulls out this coefficient minus I over h bar times h. So minus I times I is equal to 1, h divided by h is equal to 1, so we're just going to have h e to the power minus I h bar h times t, which indeed is equal to h times u. Therefore, indeed, so we satisfy the required Schrödinger equation. So an interesting and sort of attractive feature of this evolution operator is that it solves the Schrödinger equation with all possible initial conditions in one go, because the evolution operator itself does not actually depend on the initial conditions. So we see that it has a universal initial condition. At t equals 0, u is equal to 1. So for instance, here in this geometrical interpretation, if we had, let's say, different psi of 0, let's say this will be psi of 0, prime. So the evolution of this other initial condition in this sort of Hilbert space would be a rotation by the same angle around the same axis, well, to a different psi of t, let's say psi t prime here, but the evolution operator that would enforce this rotation will be exactly the same as before. So it will be exactly the same u of t. So in our case in particular, so we're interested in knowing how this particular initial condition evolves with time, and therefore the wave function would be equal to e to the power minus I over h, Hamiltonian times time, acting on this initial condition. So this is sort of a exact and universal solution of the Schrödinger equation, whatever it is, with this initial condition of a localized particle in a certain region in space. Now let us go back to the main question that we posed in the beginning of this segment, namely the question about the overlap between the wave function psi of t sort of propagated from the vicinity of the point r sub I and the wave packet localized in the vicinity of the point r sub f. So what we found in the previous slide is a formal exact expression for this psi of t. So psi of t is the action of the evolution operator on the initial condition r sub I, and therefore if we put 2 and 2 together, the expression for the propagator is going to be the following matrix element. It's going to be Rf. Here we're going to have this evolution operator ht r sub I. So this guy is simply this psi of t. And so we get the expression that we're actually going to use in the next segment to derive the Feynman path integral. So Feynman path integral is another representation of this matrix element between Rf and Ri of this operator u of t. So at this stage you may ask me, why would we bother to look for any other expression for the propagator apart from the one we just derived, which looks pretty compact and simple? So the answer to this is that this simplicity is deceptive, because the main object here, this evolution operator, involves exponentiating an operator, the Hamiltonian. And to actually calculate such an exponential of an operator, exponential of a matrix, is a rather complicated exercise. And in general, even to define the exponential of an operator is a tricky business. So as a side comment here, let me remind you that for an arbitrary operator, a matrix X, in our case this X is this minus I over h bar ht, so its exponential is defined via the Taylor series. So it's 1 plus x squared over 2 plus x cubed over 3 factorial plus etc. And so to calculate this series with matrices operator is rather complicated. And so the Feynman approach, as we will see, essentially circumvents the need to calculate this complicated exponential and truncates the series right here. Basically the end result, as we will see, will be an expression that doesn't have any operators whatsoever. And not only that, the final result also will have a very clear intuitive interpretation that we already sort of advertised in the beginning of this lecture.